part of keeping them separate is making them look separate. So if you make sure that you're writing all your steps really carefully, then they're not going to ever look the same, because you won't, if you're writing your denominator every time when you add and subtract, then you're never going to have a step that doesn't have a denominator like you will when you clear fractions. So that's one of the reasons I'm on you guys so much about your notation, is just that it's what helps us distinguish between things that are different. And if we accidentally make things look the same that aren't the same, it's really easy to get them mixed up. And they're already kind of similar. So let's just look at two problems kind of side by side so we can look at the difference between solving the two types of problems, and then we'll get into sort of more complicated equations. So we are solving, this is 5.5. We're solving rational equations. So we're going to do two examples. We'll do one where we're going to simplify. Two-thirds minus 5/6 equals 1 over x. And then we will solve. Two-thirds equals, very nice equal sign, equals 5/6 plus 1 over x. So let's start with the simplifying. That's the type of problem that we've done so far in this unit, where we are just rewriting that expression. Oh my gosh. It sort of ruins like the entire point of this whole conversation. Make sure that you, in that first one, that there's a plus there, not an equals there. So the big difference between the two is there's subtraction here and an equals here. So just double check that they're written correctly. Okay. So we have an expression here on the left. What we've done so far is get common denominators and rewrite the expression just in a different form. We're not trying to find the value of anything. We're just trying to rewrite the expression, which means we can't change its value, right? If we do anything to it that changes its value, then it just becomes a completely different expression. And so it's sort of pointless to try to talk about it in reference to this expression. So when we simplify an expression with fractions in it, I can spell expression. We get common denominators. Don't really have room to put that right there. So our goal is to make the denominators the same. And the only way we can do that is to multiply individual fractions by some version of the number 1, right? So some fraction that's the same on the top and the bottom, that will give the fraction the denominator we want without changing its value. So in this case, my LCD is going to be 6x, right? I need a factor of 3 from that first denominator, a factor of 2 to get 6 for the second denominator, and then a factor of x from the third one. And so we're going to multiply. We'll do 2/3 times 2x over 2x minus 5/6 times x over x plus 1 over x times 6 over 6. So that everybody has a denominator of 6x. And so now we can combine our numerators. So we get 4x minus 5x plus 6 all over our common denominator. Notice our denominator didn't go away, right? We still have a denominator in every single one of our fractions. And then we can simplify the numerator. We get negative x plus 6 over 6x. And that can't be simplified anymore because this is addition, not multiplication, right? In the denominator, I'm multiplying 6 and x. And in the numerator, I'm adding 6 and negative x. So I can't cancel those 6's because they're not both factors, right? In the numerator, that's a term, not a factor. And so it's part of a bigger factor.
You wouldn't want us to take out the negative 1 and make it negative 1 parentheses x minus?
You could do this. The only reason I didn't is that it doesn't actually help me simplify it all.
Okay,
so yeah, it's fine. If you can see that nothing is going to cancel, it's fine to leave it. The taking out the negative 1 and putting it in descending order is basically part of factoring. So when I look at negative x plus 6, I know there's not going to be something to cancel downstairs in the denominator because there's no addition or subtraction. So it's impossible for me to cancel something with addition and subtraction in it with something that doesn't have it. So that's the only reason I didn't go through the process of factoring the numerator. But yeah, that would be totally acceptable either way. So now let's look at this equation. So the difference here is that I have an equation I want to solve, which means I want to find the x value that makes it true. And we have a lot more leeway working with equations than we do with expressions because I can do anything I want to one side as long as I do something equivalent to the other side. So if I want to make the left side 500,000 times bigger, that's fine, as long as I also make the right side 500,000 times bigger. So unlike expressions where I can't change the value of anything, in equations I can change the value all I want as long as I keep it balanced, which means that I can multiply everything by the same thing, which will make all my denominators cancel. And so that's what we've done before, clearing fractions when we have denominators or when we have fractions in equations. So we are going to, because this is an equation, we're going to clear fractions. So our goal when we clear fractions isn't to make all of the denominators the same, it's to get rid of all of the denominators. So my LCM is going to be the same thing. It's still 6x, but I'm using it in a different way. Instead of trying to make all of the denominators 6x, I'm going to multiply everything by 6x over 1. That's going to allow me to cancel all of my denominators. So we have 6x over 1 times 2/3 equals 6x over 1 times 5/6 plus 6x over 1 times 1 over x. And the differences in this first step are that's the main source of confusion between the differentiating between the two different types of problems. So you want to be really clear about when you're multiplying by the LCM over 1 and when you're trying to make all the denominators into the LCM. So one way that you can think about it is with equations, we multiply by the same thing on the left and right side of the equation, whereas in expressions, we multiply by the same thing on the top and bottom of each fraction. So you're sort of multiplying by the same thing on both sides either way, but in one of them it's both sides of the equation as opposed to both sides of the fraction. And here, because we have two sides of the equation, that fraction that we're multiplying by doesn't have to be the same on the top and the bottom. So now we can go through and start canceling stuff. So we can cancel a factor of 3 here, a factor of 6 here, and a factor of x here. And if you look across the bottom, notice that every denominator other than 1 got crossed out. And that's our goal here, is to get rid of all of our denominators. And we end up with 4x equals 5x plus 6. And we'll subtract 5x from both sides, get negative x equals 6, and x equals negative 6. So you can see some similarities if you look at them, like the 4x and the 5x and the 6. But the big difference here is that we still have a fraction in every single step here. Like we could have some like miraculous coincidence where you end up getting to cancel the denominator and like your final answer isn't a fraction, but that's so very rare. Like if you're adding and subtracting fractions, your answer is almost always still a fraction. Whereas here, after that first step, we no longer have any fractions. So, like I said before, one of the keys to keeping these separate and not getting them mixed up is just making sure that you're really writing what you mean, right? That like when you multiply by 2x over 2x, you don't write just 2x, right? You actually write 2x over 2x. It seems tedious, but I promise that I get no joy out of making you guys do things that you don't need to do. So everything I ask you to do, it's like I have a good reason for it, I promise. And so like if you write everything exactly as you mean it, then it's a lot easier to keep everything separate and not get them mixed up. So one other thing we can notice about, if we focus on this equation for a little bit, one other thing we notice is that what would happen if, I shouldn't put it there, if I tried to plug in x equals 0 in this equation. Yeah, it would make a denominator 0, right? Which would make the right side of the equation just not even exist. So like there's lots of numbers I could plug in that wouldn't make the equation true, but this is even kind of a bigger deal than that, because not only does it not make the two sides equal, it makes one of the sides just not exist at all. It has no numerical value, which sort of blows the whole thing up. So if x was equal to 0, the right side would be undefined. So we call 0 a restricted value. And we found restricted values before when we were finding the domain of functions that involve division. Restricted values are just any values that would make one or more of the fractions undefined. And those can never be solutions to the equation. And so we will find those ahead of time so we can compare our solutions to them later on. So let's go through the steps now for finding or solving these guys, and we'll do an example along with it. So we have equations. That got away from me. So let's do do 2x for x minus 3 6 over x equals 18 over x minus 3. Nope. X squared minus 3x. Okay. So my first step, just like when we're adding and subtracting rational expressions, is to factor the denominators. Because like we saw in the last couple examples, like we're still finding the same LCM, we're just using it a different way. And remember that the first step to finding an LCM was to factor everything. So we'll start by factoring our denominators. And so we have 2x, and x minus 3 doesn't factor, so I'm just going to put it in parentheses. And then x is a monomial, so it's not going to factor. And then over here I have a GCF of x, so I have x times x minus 3. And then our next step is going to be to figure out what our LCM is. What's my LCM here? Yeah, I need a factor of x minus 3, I need a factor of x, and then that takes care of all three of those fractions, right? So we're going to find our LCM. And then the next thing we're going to do is find those restricted values. So I want to find any values that are going to make the denominator 0. And this is really just like when we found the domain of functions, was any denominators, we set them not equal to 0. However, I don't really want to do it 3 times. Like I have 3 fractions. I don't really want to set each one individually equal or not equal to 0 to find these. But since my LCM contains all of the factors from each of my denominators, it suffices to just set your LCM not equal to 0, and that'll find you all of your restricted values, like for each individual fraction. So we're going to find our restricted values. Uh-huh. Good. By solving our LCM not equal to 0. So we'll just write those over here. And you don't have to, you can do this in your head for sure. I just want to write it down, how we found it, for anybody that's not sure. So then we set each factor not equal to 0. And we got x is not equal to 0 or 3. And I think it's really important with these to make sure you put that slash through the equals, because since we're solving equations, we're also going to have x equals numbers down here, and it's really easy to get them mixed up if they both say x equals. So you want to be really clear about which are the numbers x cannot be equal to and which are the numbers that x actually is equal to. So now we're ready to clear fractions. So we are going to clear fractions. By multiplying both sides by the LCM. And remember, it's the LCM over 1. So we're multiplying everything by the same exact thing. In this case, x times x minus 3. So we have x times x minus 3 over 1. That's my LCM. And we're going to multiply that by my first term minus x times x minus 3 times my second term equals x times x minus 3 over 1. Third times a charm. My last two, I've run out of room on that every single time I've done it today. So now we can go through and cancel. So one good general rule about like doing a problem sort of methodically and not like getting yourself all tripped up is not trying to like think ahead. Like, don't worry about what this is going to be equal to until you just write it down. So like, you know, just do the step of multiplying everything by the same thing without worrying about what you're going to end up with. And then you can go back through and start canceling stuff. And that way you're not like always trying to like think 2 steps ahead as you're doing one step. And so that can get you kind of lost and mixed up because like I noticed on the homework last night, like a lot of people were multiplying by 1 over h, like in the same step that had an h in the denominator instead of like writing a new step. And I think it's just because you're kind of thinking ahead as you're going instead of doing each individual step, but it can really kind of mess you up if you do that. So now that we've got it all written out, now we can worry about what we're going to get from it. So we can cancel this x minus 3. We can cancel that x, and then both of them cancel here. And then again, just like we saw in the last example, if you look across the bottom, so in all the denominators, everything except for 1 canceled. And that's our goal, right, is to get rid of all those denominators. So now I'm just going to write down what I end up with without trying to, like, again, without trying to do any distributing or calculations, because this is where you can make sign errors really easily if you kind of distribute, like, too fast. So I'm just going to write down what's left over, and then I'll worry about what I'm going to get from it. So I have x times 2x minus 6 times x minus 3 equals 18. And so now I'll go through and do any distributing or multiplying I need to. So we have 2x squared minus 6x plus 18 equals 18. And my next step is just to solve this equation. So we're going to solve the resulting equation. So I always ask myself first what type of equation it is, right? Because we take a different approach if it's a linear equation versus a polynomial equation with degree higher than 1. So here we have an x squared, which means we want to get a 0 on one side so we can factor the other side. So we're going to subtract 18 from both sides, which gets us 2x squared minus 6x equals 0. And then I want a product on the left, so I'll factor. We have a GCF of 2x. And then set each factor equal to 0. And we get x equals 0 and x equals 3. And so then this is where those restricted values come in. Our last step is to compare our solutions to the restricted values. And eliminate what we call extraneous. Something solutions. So an extraneous solution is a solution that we got solving correctly, but doesn't actually work in that original equation. So like, can x be 0? We found out above that x can't be 0, right? Can it be 3? It also cannot be 3, which means this equation has no solution. And so both of those are what we call extraneous solutions. And where they come up is they come up in equations that contain operations that have restrictions on them. So remember when we were finding the domain of functions, we said there's restrictions on numbers that you can divide and numbers you can take the square root of. And so any equation we have that has division or square roots in it, it has the possibility of having these extraneous solutions. Because 0 and 3 are perfectly good solutions to this equation, which is what we got after we cleared fractions. They just don't happen to be solutions to this equation because that equation has denominators in it. And so plugging 0 or 3 in will make that whole thing just not exist. And when we clear fractions, like our equation doesn't know that it used to be an equation with denominators in it, right? And so we get solutions that work just fine in that middle equation because there aren't any denominators there. But then when we try to go back in the original one, it doesn't actually work. And so we have to throw those out. And it's possible to, if you get two solutions, it's possible for them both to work. It's possible for just one of them to work. It's possible for neither to work. So there's no rule about always having no solution if one doesn't work. You check each one individually. So I also thought it might be interesting if we just look at kind of what this looks like on a graph. Like if we were to graph the left side and the right side is two separate functions. We know that where they intersect would be the solution to our equation, right? That would be where their outputs are the same. And it's always just kind of interesting to see what it looks like to have no solution in this case, because they're not lines, so it's not like they're going to be parallel, right? Because this is nonlinear. So it's kind of cool just to see what it looks like. I think I actually have just about the general process. Anything come up as we were doing those? Good? Okay, let's do some more. And again, similar to all the other problems we've been doing in the past week or so, these are a little bit tedious, but I promise you taking your time and writing out all the steps saves you time in the long run because you don't have to do it 5 times because you made a silly mistake. So just take your time with these and go nice and slow. So we'll do one more together and then you guys can try one. Let's do... solve. Make sure I copied that right. There we go. Okay. So again, we're going to start by factoring all our denominators. So we have x over x minus 2 doesn't factor, so we'll just put it in parentheses, plus x squared minus 4 is the difference of squares. I noticed on the homework last night that some people weren't recognizing that that can be factored. So be sure that you're on the lookout, especially in these problems. It seems like the textbook really likes to use the difference of squares in these problems. So make sure you're on the lookout for if you have an x squared, subtraction, and then a perfect square, those can always be factored. And it gets quite messy if we try to do this without factoring because our LCM ends up way bigger than it has to be.
So that's an x. And then equals, and I have an LC or a GCF of 2 and 2x plus 3. So what's my LCM going to be?
2x minus 2x plus 2.
Mm-hmm. So we need a factor of 2, and then x plus 2 and x minus 2. Very good. And so then we'll find those restricted values. And we do that just by taking our LCM, so just you can just copy it. And then set that not equal to 0. And you can definitely do that in your head if you want to. You don't need to, I mean, I want you to write down what the restricted values are, but you don't have to show the whole solution if you can do that in your head. So 2 is not going to contribute a restricted value because our GCF, it doesn't have an x in it, right? And so it's not going to ever be equal to 0, so we don't have to worry about it. So we have x plus 2 is not equal to 0, x minus 2 is not equal to 0. So x cannot be negative 2 or 2. And I'd really like to see you guys, like on the test, write out that little square. Just, I mean, it doesn't have to be a little square, but write that little bit just like I did. Because then if everything else like just goes to hell, like that's a good 2 points there, just showing me that you knew you needed to find an LCM, that you knew there were restricted values and you were able to find them. So it's always good to just write it all out rather than trying to hold it in your head anyway. But you can get partial credit for it even if everything else
Can x
falls
also
apart.
equal 0?
So x can be 0 because there's no x in my GCF. So the only way we'd get a 0 there is if we had like 2x as a factor. Because if you put 0 in, you get 2 times negative 2, which is negative 8. So if our GCF had been like 2x, then 0 would be a restricted value. Good. Okay, now we're ready to clear fractions. So we're going to multiply by 2 times x plus 2 times x minus 2 over 1. Oops. And then plus, same thing. And on the other side. And notice, just like everything else we've done with these guys, I'm putting the numerator in parentheses if it has addition or subtraction. That's going to help me when all my denominators go away and I have to distribute. That's going to help me to not forget to distribute correctly, right? If I don't have parentheses, I'm going to end up with a different multiplication problem. Oops, that's a 2. Okay, so now let's go through and cancel. So here I can cancel an x minus 2. Here I can cancel x plus 2 and x minus 2. And then here just the 2 and the x plus 2. So let's write down what we're left with. We have 2. And I'm going to bring that factor of x to the front. That way I don't have to try to distribute the x and the 2 separately. I can distribute like 2x all at once. And then plus 2 times x equals x minus 2 times 2x plus 3. now we have a lot of simplifying to do on the left and right. So we'll get to distributing 2x squared plus 4x plus 2x equals 2x squared plus 3x minus 4x minus 6. And at first glance, this looks like it's going to be a quadratic equation, right? Because it's got an x squared in it. But if I think about getting a 0 on one side, the first thing I would do is subtract 2x squared from both sides. And then I see that they both just go away. So really, this is like a linear equation in disguise. Because subtracting 2x squared from the left gives me just 4x plus 2x. And from the right just gives me 3x minus 4x minus 6. So I no longer have that x squared. So now I'm just going to combine like terms. And then this is just a linear equation, so I'm going to get all terms containing x on one side and all terms not containing x on the other side. So we have 7x equals negative 6, and x equals negative 6/7. Is that a valid solution? That works, right? Because it's not negative 2 or positive 2. And so that's the solution to our equation. Okay, here's one for you guys to try. Let's solve okay, give that one a shot. Bring our denominators. And this one factors into x minus 1 times x minus 3. Pro tip, when in doubt, if you are not sure on factoring, like, in order for these to work out nicely, like, that one's probably going to be both of those. Like, otherwise, if it was two completely different factors, this thing would turn into just a mess when we try to clear fractions because we'd have so many factors. So, it always kind of works out that way, or else we'd end up with an equation that we can't really solve. Okay, so then we're going to clear fraction, or our LCM is x minus 1 times x minus 3. What are our restricted values? Yep. 1 and 3. So then we'll clear fractions. We have x minus 1 times x minus 3. Remember, multiplying everything by the same thing, right? We're not trying to change the denominators. We're trying to get rid of them. Minus 3 over 1. And so now we can do some canceling. So we've got x minus 3, both of those, and then that. So here we get 6 times x minus 1. And then what happens to that second term?
Yeah, it's just 1, right? We can't get rid of it completely because it's not 0.
So we just get 1 over 1, which is just 1. And then on the right side, we have 5 times x minus 3. So we'll distribute. And combine like terms. And then again, we see that this is a linear equation. And so we're just going to get all terms that contain x on one side and all terms that don't contain x on the other. So subtracting 5x from both sides gives me x. And then adding 7 to both sides gives me -8. Is that a good solution?
All right, so it's not one of our restricted values, so we keep it.
My office hours today,